Okay, the purpose of this video is to explain the math behind data prediction. What we've been doing in the Python videos is we put in the command polyfit and it draws a line through the data, or you can get it to draw a polynomial through the data, which is easy, but we want to explain what the computer is doing because math is interesting and we might want to not use the polyfit command, rather design our own way for the computer to examine the data and write our own code using the math. And so that's what we're doing here, is we're going to talk about the data, talk about the math, and hopefully get maybe Hythloday involved a little bit because he likes talking about math. So what it's called is OLS, ordinary least squares regression, and that fits a line to the data. In order for that to work, we have to meet a number of assumptions. There's about 10 of these, depends on how you count them. A lot of these assumptions are very similar to each other and can be combined into one assumption, or the assumptions can be broken down into more specific assumptions. So there's not really a set number of Gauss-Markov assumptions. But the thing is, none of these assumptions they're rarely met in the real world. Like one is no heteroscedasticity. That's the hard word to say. It has to do with the variance. That the change in variance as x changes is going to be 0. Like that the variance isn't going to change as x goes bigger. We've seen this in Mad Coder's coding videos, where he's programmed the data to fit a line, but as that line gets more and more and more, the data gets more spread out. And this is when you see heteroscedasticity, then there's probably some omitted variable bias going on, right? That there's something correlated with x that is also affecting y, and that's why the variance is changing as x gets bigger. Now, perhaps the omitted variable is something that we can't observe. It's not measurable, so then we couldn't include it. Or perhaps there's something about this data that as x goes bigger, the volatility, the variance gets more spread out, and that's just part of the actual function, in which case the answer is to try and weight the observations that are closer together, because they're more close to the actual relationship, where these ones are more spread out and we're not sure where the relationship is within that. Another Gauss-Markov assumption is that the underlying source function must be linear, right? If we've got data that's curving and we draw a line through it, obviously that's not a good prediction. What we're going to want to do there is bend the data so that it is a line, draw a line through that, and then bend the line back down using the inverse of the technique we use to bend the data, so the line bends down again and will fit the original data again as a curve. Or you could maybe use some nonlinear prediction. But with the ordinary least squares, we're starting with lines. So a line is commonly written mx plus b, but we're going to use some different notation, right? We're going to have the y be the same, and this b is going to be beta naught, is the y-intercept. And m is going to be beta 1. It's the slope of the line. And then u is another constant, and it relates to the unobservables or the error. It basically relates to this variance, that the data isn't going to lie exactly on the line. So it's going to be plus or minus a little bit. And that's our u. Now, beta naught and u are both constant. So often these things, when you're looking at data, it can be hard to separate them, because one constant plus another constant is a constant. and so they can kind of get squashed up together. So that's something we have to look out for. Now there's going to be some more notation. Our prediction line, like this is the underlying source that we're trying to estimate. Our estimation of that is we're going to put hats on everything. So y hat equals beta naught hat plus beta 1 hat times x plus u hat. That's our prediction line that we're trying to predict the source line with. And then also some notation is for the average values. We're going to use a bar. So y bar is the average value of y, x bar is the average value of x, and u bar is the average value of u. So what we're trying to do is find beta 1 hat, which is our slope predictor. We're going to need some assumptions. What I'm doing here, this is a algebraic proof, and we're going to need some Gauss-Markov assumptions to do it. U has to be normally distributed around the source, right? So if there's some line going through this, the error term has, is going to be in the middle of this, and the error is going to be the same on either side of the line. Like the amount of that the dots go up from the line is equal to the amount that the dots go down from the line. So our expected value of u is 0 because it goes up as much as it goes down. Our next assumption is going to be no heteroscedasticity, so that the expected value of u given x is the expected value of u. That u, we're not going to expect it to change as x increases, right? And our expected value of u, of course, is 0, right? And then our third assumption is that our source is linear, that our source that is creating the data is y equals beta naught plus beta 1x plus u. So we're going to start with that and set it to 0, and then take the expectation of that, which is like taking an average. Now, because our expected value of u is 0 from up here, then our u is going to drop out. We're going to multiply both sides by x, so x times 0 is still 0, and then we get an x in here. And then we'll take an average of the data, because an expectation is equal to the average. Like we would expect, like if we draw a number out of a hat, we would expect to get the average number. So sum everything up. This is our summation symbol. We're going to sum of all the xi's, which are all the individual observations, which is this x, but it's all the individual x's, times yi minus beta naught hat minus beta 1 hat times xi, it should be an I there, set that is still set equal to 0. And then since the average value of y is equal to beta naught hat plus beta 1 hat times the average value of x, then we can solve for beta naught hat and put that in terms of y and beta 1 and x, so that we can do some substitution of beta naught hat. And so beta naught hat here is now going to be this y, average value of y minus beta 1 hat times the average value of x. And so then we can rearrange that and put some on the other side where the 0 was, so that the sum of xi times the distance between the observations and the average value of y is equal to beta 1 hat times the sum of xi times xi minus the average value of x. So all the observations minus the average value. And then we're going to solve for beta 1 hat. And so we get beta 1 hat is the sum of the distance between all the x observations and the average value of x multiplied by the y observations minus the average value of y over the sum of the xi's minus x hats squared. And And so I just want to point out that this is a distance, right? The difference between an observation and the average is a distance, and this is a distance between the observations of x and the average value of x. And then this beta 1 hat is what we're looking for. It's the slope of our predictor line. So to do that for MLS, which is multiple linear multiple least squares regression, we're going to have more data. We're not going to have just one x, we're going to have a bunch of different x's. We could call this econometrics, so that you can look it up on the YouTube and get more information about how this is done. Now, the common example that people use when explaining econometrics is the wage. Wage is equal to some intercept plus beta 1 times their level of education. The more education you have, the more we would expect that your wage would go up, plus beta 2 times age, that your age is going to be affected with your income, plus beta 3 times your parents' income is related with income, plus u is our unobservables or our error term. And now notice that beta 1 and your level of education and your parents' income are probably also correlated. So there's going to be some issues with that we could get into, but we're just going to basically get in. I'm setting that up as just a example of how to do multiple linear regressions. So basically, to put this as a model, y equals beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus u. And so our goal is to minimize the distance between the line that we fit and all the data observations, right? And so we want to minimize the sum of squares. The sum of squares is our distance. So we want to minimize the sum of yi minus beta naught, like it's basically all set to 0. This is just like doing the Lagrange, as we've said before. Like yi is equal to all this stuff is the same thing as yi minus all this stuff is equal to 0, right? So we'll take the derivative of this in terms of all of our betas and set each of those equal to 0, right? So you got the derivative in terms of beta naught equal to 0, the derivative in terms of beta 1 set equal to 0, derivative of beta 2 set equal to 0, derivative of beta 3 set equal to 0, and then solve, that gives us a system of n equations and n unknowns, and we solve the system to get our betas. That's not a formal proof. I'm just kind of briefly going through what the math works. It's just like doing the Lagrangian, as I did in a recent video where I made an economic model in Python. And it's the same kind of idea where we take all the different derivatives so that we get a system that's of optimized values, and then we can solve that system and it'll give us the multidimensional line that we want to get. But now computers hate calculus. They're going to do this as a matrix problem. And so I'm going to really briefly do some linear algebra review and talk about how the matrices work. First of all, there's an identity matrix. It's basically, a matrix is a grid with numbers in it, and that's all a matrix is. It's basically like a multidimensional hypernumber. Now this one here is called the identity matrix. It's got ones along the diagonal and zeros everywhere else. It has to be a square matrix to be an identity matrix. And that's basically saying 1. Like this is how to say 1 in the third dimension, is with this identity matrix. So with operations on matrices, we're going to need to multiply them together. And it's very similar to the way the dot product was done for the vectors I did in Inventive BS number 2. where it was, like this vector times this vector is this times this times plus this times this plus this times this. But with a matrix, it's going to be rows by columns. So we're going to, like, these should all be numbers, but I marked them A, B, and C and whatnot so that we could keep track of it all, right? So to get, it's going to, like a 3 by 3 matrix multiplied by another 3 by 3 matrix is going to result in another 3 by 3 matrix. And to find this first entry, basically it's A, we're going to do rows by column. So A times 1 plus B times 4 plus C times 7 all goes here. For this one, it's the second column and the top row. So it's B times 1 plus E times 2 plus H times 3. We'll keep doing this a little more. This one's going to be the first row times the, am I doing this wrong? Yeah, I did that wrong. I'm already screwing it up. Anyways, that's the idea of matrix multiplication. We're also going to need a transpose of a matrix, and that's just turning the matrix on its side, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This one's 1, 4, 7, 2, 5, 8, 3, 6, 9. So the 1, 2, 3 goes down where 1, 2, 3 was going across before. And that's the transpose matrix. We're just going to switch it. And we're also going to need an inverse matrix. And an inverse matrix, let's say we've got some matrix A, and we multiply it by its inverse. That will give us the identity matrix. Basically, an inverse is a way to cancel out a matrix and have it just become 1. And so it just kind of makes it disappear when we're doing multiplication, because multiplying something by 1 is just itself, and that'll make more sense as we go on. So I'm going to tell you how to find the inverse matrix. We're going to do something called Gaussian elimination. And we use the Gaussian elimination on a matrix such that it will turn into an identity matrix through a series of procedures. Now, whenever to find an inverse matrix, we're going to have a matrix that we want to invert. It has to be square to have an inverse. Square meaning it's got the same number of rows as the same number of columns. And then we're also going to have an identity matrix. And whatever we do to the original matrix to turn it into identity matrix, we also do to the identity matrix. And when we're done with it, this one will look like an identity matrix, and this one will be the inverse of the matrix of this original matrix. So I'm going to tell you how to do Gaussian elimination really quickly. There's two things we can do. We can scale rows, and then we can add scales of rows together. And we're going to do an example to show you how that works. So our goal is to turn a matrix into identity matrix. And we'll start with the first corner in our identity matrix, right? We want that to be a 1, and it's already a 1. So, hey, we're already a step ahead of the game. And then we're going to move down one to this 4, right? Now to get this 4, it wants to be a 0. So we're going to multiply, we're going to take 4 times the first row and subtract it from the second row, and that'll give us 0 here, right? Because 4 times 1 minus 4 is 0. 4 times 2 minus 5 is 3. That's wrong. And then 4 times 3 is 12. Minus 6 is 6. And then we're going to want this to be a 1, right? And it's 2 right now. So we're going to take 1/2 of the first row and subtract it from the second row. No, we can just scale it, right? We can do scaling. So we just take 1/2 of row 2, and so this was a 2, and now it's a 1, and this was a 6, and now it's a 3. And I'm going to keep doing that kind of thing until this is identity matrix. Now, whenever we do one of these things, we're also going to want to have one of these identity matrices over here and do that same thing to the identity matrix, such that at the end of this process, the identity matrix will be the inverse. Okay, so now that we have all the tools, we can think about data as a matrix. So when we've got a data set, it is a big grid with numbers in it, right? So our observations go in it. So like we're going to have a column of our education, that's going to be x1, a column of ages, that'll be x2, and a column of our parents' income, that'll be x3, and there'll be all the different observations in here. And then wage, right? So this top person, he makes a wage of 4. He's got an education of 1. He's got an age of 3 and a parent income of 5. I know those aren't real numbers. I was just using simple numbers, but that's the idea. And then our second person has an education of 2 and an age of 4 and a parent income of 5, and his wage is 8. And so then we also have if we multiply this matrix by our beta knots, then we get our wage. And we want to kind of solve for these beta knots, or the betas. Now, one thing I forgot to mention here is I didn't include beta knot in this, but we could have beta knot in our variable vector by having a column of 1s. Adding a column of 1s on the side of this matrix will make it so like 1 times beta knot, and then 1 times beta knot, and then 1 times beta knot. So we always have a beta knot in there, our y-intercept. Now, notice this is an overdetermined system, right? We've got 4 equations and 3 unknowns. So there's going to be no solutions to this problem. What the line is the closest solution to the problem. You know, if it was square, we could use that Gaussian elimination system I just taught you to solve the system. But since it's not square, that's our problem. So what we're going to try and do is make it square. Here's the same thing written out just to make it more simple. I'm going to just name all the matrices. So our one with all our observations in it, we're going to call D for data. Our variable vector is going to be called our betas, and then the explained variable is going to be our y vector, and we're going to need this to be square. Now, what we do to make it square is we'll multiply it by its transpose, and if we do that, then we also have to do it to the other side. So then we also have to multiply y by data transpose. And that makes this square. So now we've got a square matrix. I'm calling data transpose times data times our variable vector equals our data transpose vector or matrix times our y vector. And so then we're going to find an inverse of this square matrix and multiply both sides by that inverse, right? When we multiply these guys together, that basically becomes 1, right? So then it'll go away, and it's just our beta vector is equal to the D transpose D inverse times transpose of D times Y. So now we've got our B's isolated, and you just have to do all this matrix multiplication, and we can get our line. So that's how the computer likes to think about the math. Now let's talk a bit about, we can also use this matrix method to do best fit polynomials. So here's an example of some data, and it's going to go in a curve, right? So we've got an observation of when x equals 0, y equals 0. We've got an observation of when x equals 2, y equals 3. We've got an observation when x equals 3, y equals 4. And then this observation when x equals 4, y equals 2. Right, come across here. So to include our beta knots, we've got our beta knot this time, so I add this column of 1s here. And so then we have a column of here's all of our x things. So this will be the same as this column here. We'll be right down here. And then this is all of that squared, right? So that our model that we're doing with this is y equals beta naught plus beta 1 times x plus beta 2 times x squared plus u. And that'll give us our polynomial, right? So here it is. We've got our 1's, and then here's our same x column, 0, 2, 3, 4. And this is all of those values squared. And then here's the y's, our y vector here. And then we'll crank it out as I showed you on the first page and find our coefficients to our polynomial. But we're not limited to lines in polynomials either. This last slide is, I'm going to do a couple other shapes. We can find a best fit circle, and that's can be easy, can be hard, depends on how you do it. I'm going to do it the easy way here, right? So if we want to fit a circle to this data, the center of that circle is going to be the average value of x and the average value of y, somewhere in the middle there. And then our radius of the circle will be the average distance from all these points to that center, and we'll fit a circle to the data. And another idea I'm really into is something I've been thinking about called the best fit ellipse, where we draw an ellipse in the data. And the reason I like that is the ellipse has some slope to it, so we're measuring the slope of the data, plus it spreads out, so we can measure the variance of the data as well with the ellipse. Okay, I think that video was pretty boring, but I hope you got something out of it. Anyways, thanks for watching. Oh shit. Oh wait, okay. How do we stop it? This one.